Hello, everyone. My name is Chen Ouyang, and I'm from Queensland University of Technology in Brisbane, Australia. On behalf of the authors team, I'd like to share with you our work on generating purpose-driven explanations. In our study, we're interested in generating explanations for predictive models. The broad area of research is known as explainable artificial intelligence, or XAI. In simple words, XAI intends to provide explanations about why a certain decision was made by a predictive model underpinned by machine learning or deep learning techniques, mostly considered as black box models. By doing so, XAI aims to address the purposes such as providing model transparency and ensuring fairness in autonomous decision-making. In this paper, we focus on generating explanations for the purpose of model inspection. We follow common practice of model inspection, which starts from identifying part of the model for inspection, analyzing the issues, arriving at primary diagnosis, extracting insights about underlying causes, and coming up with recommendations for model improvement. With a focus on predictive process analytics, we propose a conceptual framework for generating model explanations. It starts from model development, which takes event log as the input and follows a standard approach for data mining. Then at the various stages of model development, we extract primary explanation on how models make decisions and support explanation to provide evidence. Often these explanations are abstract and need to be contextualized. For example, what is the granularity of explanation and what insights to be extracted that will be useful to end users? Finally, the consolidated explanations are presented to the target audience using an appropriate presentation technique. In the following, we will elaborate on this conceptual framework. As mentioned before, after predictive model has been developed, explanations can be extracted at various stages of model development. These mainly include primary explanation, which focuses on how models make decisions, and support explanations, which focuses on explaining input data, providing support evidence, and incorporating relevant domain knowledge. When extracting primary explanations from models, we may have white box models, such as a decision tree or a linear regression model, in which case explanation extraction can be straightforward. But often we're faced with black box models, such as tree ensembles, support vector machines, or deep neural networks, in which case we need to apply model explanation techniques, such as incorporating explainability within a predictive model supported by intrinsic techniques, or developing a separate white box model to mimic the decision-making of a black box model supported by so-called post hoc techniques. Based on what can be extracted from model and data, explanation consolidation aims at generating meaningful insights to end users. First, what is the granularity of explanations? Explanations may be needed for inspecting model behavior on a single data sample, such as a single process trace. These are known as local explanations, and often they're useful for anomaly detection. Sometimes, explanations about overall model performance on the entire data set are needed, and these are known as global explanations. In addition, we also propose so-called cohort explanations, which focus on model behavior on a subgroup of data samples sharing similar characteristics. For example, process traces that were always overdue or beyond the budget. Next, given the different levels of explanation granularity, useful insights to extract include the findings about model symptoms and the potential underlying causes for the symptoms. For example, for the purpose of model inspection, often poor model performance is seen as a typical symptom. Potential causes for poor performance may be identified by examining primary explanations on how models make decisions. Identified causes can be further validated with the support evidence that may include domain knowledge and descriptive statistics of data samples. Finally, presentation of consolidated explanations can be supported using an appropriate technique such as visual natural language-based, algorithmic, and counterfactual techniques. The exact technique to be chosen depends on the nature of insights to extract and the target audience. On top of explanation presentation, it is also interesting to consider human-centric explanation, which aims at how to make explanations convincing, persuasive, and social to human users. Guided by the proposed conceptual framework, we have built an interactive visual explanation interface, which can be accessed at this link. A main screen of the interface provides an overview of different panels supporting explanation granularity levels and various insights. The example used is a publicly available real-life event log capturing the execution of a loan application process at the Dutch finance institution. Next, the first author, Bamali, will give a quick demo of this visual explanation interface in the context of this example dataset.
We have implemented a model explanation visualization for a process next event prediction model that uses primary and support explanations for model inspection. The underlying dataset is an event log of a loan application process, and the predictions are made at two key decision points of the process. The two decision points are event A pre-accepted and the event W calling out a sent offers. The top left hand table shows the model recall by ground truth, and the top right hand table shows the number of predictions, whereas the bottom left hand corner table shows the model precision by the actual prediction that was made, and the bottom right hand table shows the number of samples that were made for each prediction. So if we look at the model recall, we can see for the two targets of A accepted and A cancel decline, we have 0 recalls. Whereas the actual number of samples in these two targets are 570 and 80. That means it's a considerably high number of samples when you look at the total number of samples in this cohort. That means this decision point, which actually reduces the overall model accuracy. Then we go and see what is happening at these targets. So we can see that we select the target A accepted. We can see that the process map that leads to the next activity accepted is very simple, just 3 steps. And then we look at what are the predictions that were made when the ground truth is A accepted. So the only prediction that was made is the W filling in information for the application. We click that and then see what is the feature contribution looks like. So the bottom two visuals show the feature contribution. This is more like a cohort level explanation for all the samples that we select using these drop downs. So the left hand side table basically averages out the feature contribution, whereas the right hand side table calculates the top 2 features based on the sample size. So when we look at both the visuals, we can see that the feature role 112 occurring at last time step has a very high bearing towards the prediction being W filling in information for the application when the ground truth is A accepted. Then we look at why this is. We look at the actual target of W filling in information for the application. We look at that, the process map looks same, the feature contributions look same. So we can kind of diagnose that it could be the case that the process traces that leads to each of these targets would have looked exactly the same in terms of the resource and in terms of the activity labels. And the third feature that we use is the time elapsed. So then we use support explanations. Basically, in this particular visualization, we only use descriptive statistics of the event underlying event log as support explanation. We use support explanations to further strengthen our claim. So we select the cohort, we look at all the time steps, and we look at when the ground truth is doubly filling information for the application, and then we compare it with A accepted. Basically, the distribution of activity label, the distribution of resource, and the distribution of time elapsed look identical between the traces. So, our diagnosis is that the model performs bad for these particular targets because at this particular decision point, majority of the traces look quite identical. So the model cannot we cannot expect the model to make a good judgment based on the data that is given.
I hope that you have enjoyed the tool demo, and now this brings to the end of our presentation. If you are interested in our work, please check out our research initiative on XAMI, which stands for Explainable Analytics for Machine Intelligence. We welcome any questions, comments, and feedback from you, and thank you for your attention.